Pardon? In the what? Oh, thank you. Recording. Our goal today is to cover another methodology for risk assessment in general. We have learned already about 3 approaches. One is the concept of incidence and likelihood indices, and the second one was the risk, let me see here, the cost effectiveness analysis. Then we found ourselves working with the fault tree analysis, and we tried to hit 2 birds with 1 stone using both probability theory as well as possibility theory. Today we're going to attempt to learn about another methodology for risk assessment, and that is named event tree analysis. And we need to understand the difference between fault tree analysis and event tree analysis. Both of them use the algebra of logic that we described as having a basis of a Boolean algebra in the case of probability theory and random variables, and the De Morgan algebra rather than a Boolean algebra for the case of possibility theory. Both approaches are wonderful by themselves, but combined together, they offer us a much powerful approach, as we have seen earlier in the semester. Now, what we'd like to understand today is the difference between fault tree analysis and event tree analysis. In fault tree analysis, we started from some general statement, which we called the top event on the top of the fault tree. And then we started reasoning backwards. We took something from the general, and eventually we got specific events at the bottom here, which were really the data. So in that case, it is also called backwards chaining. Backward chaining in the language of the computer programmers. So we start from something general and we develop specific data that result in that top event. Mathematically, what we have done here is we have done basically deduction or deductive logic. And deductive logic is in fact what we are doing here, taking a top event and then going down to the bottom of what caused that top event. It is very obvious if you are doing logic that there is a reverse process in mathematics. You have seen that before probably. So you start in that case from the data at the bottom, and then you expand those data using the opposite kind of logic. Who knows what is the opposite or the conjugate kind of logic? You've done it in algebra quite a bit. Like if you have, say, a sequence like 2, 4, 6, 8, and so on, you would use a form of logic in mathematics to write a general formula. So what would be the general formula for 2, 4, 6, the sequence? Yes? Somebody should volunteer. N plus 2, right? It's increasing by 2, by 2, by 2. So this is what you have called in algebra inductive, mathematical induction, or inductive logic. So the opposite of deductive logic is inductive logic. Inductive logic, and the inductive logic is designated by computer programmers as obviously not backward chaining, but we call it forward chaining. Please take note of what's on the board because this is not in the notes if you have a sheet of paper. So this is forward chaining. If you do mathematics, it's inductive logic. If you're doing computer programmer, it's forward chaining. And that leads us to some general statement about what the process is. So you could see here that we are using two conjugate or two opposite forms of logic, the deductive logic and the inductive logic. And this is here what we call fault tree analysis. Let me write it here, fault tree analysis. And the opposite way is what we call, event tree analysis. And we need to be cognizant of both approaches, because I'll show you later that in fact, when you do the design of any kind of complex systems, you use a combination of the two, and that's what you'll arrive at today. So let us learn today about event tree analysis as a form of the inductive rather than deductive logic. All right, so let us consider event trees are not something new. They came in from what's called decision trees in operations research, and they have been used quite a bit before they have been named event tree analysis in many applications, like in aerospace, civil engineering, as well as in nuclear engineering. They have their origin in operations research, if you want to learn more about it, and in statistics as decision trees. So we'll get a decision tree as an example to introduce ourselves to event tree analysis. Decision trees are representations of a process in which the adequacy of a tree, and it is a tree because it will have some kind of a trunk, and the trunk then have lots of branches that provide more information as we move from the data to the top. By the way, before I forget, the inductive logic is also called data-driven systems in computer programming, other than forward chaining, data-driven systems. So you start here from the data and you move to make some general statements, like you start from 2, 4, 6, 8, and you say, oh, okay, it is really a sequence that is nothing than n plus 2. You start with n, 0 maybe, and then increase it 2 units at a time. Decision trees are representation of any process in which the adequacy of the tree depends on the skill and judgment of the, in that case, the safety analyst. So you'll find that, yes, we do use mathematics, we use theory, but it's also more some kind that has an art part in it. You have to learn to do it by doing it. This skill applies the event trees analysis in reactor safety studies. You'll find the analyst, the safety analyst in that case, is considerably dependent or aided by the physical entities that exist in the nuclear power plant, as and we'll show in maybe drilling for oil. That's a tree that I'm going to consider as an example of a decision tree. The understanding of any plant design and the associated physical principle, the analyst is helped to ensure a proper conceptualization for any system event tree, not necessarily just a nuclear reactor event tree. Okay, so let's study from operations research the concept of a decision tree. And let us think about oil drilling. So suppose that you're an oil engineer, a petroleum engineer, and actually you could also be a wildcatter. That's the original name for people who would go and drill holes in the ground and then get a gusher of oil coming from the ground, and they become multi-millionaires, like you have seen in the movies, maybe, or read books about it. So the wildcatter, in that case, have to take different decisions in the process of drilling and producing oil in general. So in real world, you'll find that it's a process that includes lots of art, the negotiations, selling partial rights, selling royalties maybe to get permission from a landowner or a farmer to drill on his land for oil and so on. So in that case, let us consider a final binary state that can happen for a wildcatter, an oil wildcatter. And the final state is a binary state. Binary means that comes from Latin bis, or like bicycle, biscuit. Any binary means that has two possible outcomes, and the possible outcomes are either that he finds oil or he finds no oil. See, this is a binary state, or it could be 0 and 1, in fact. Let's call that finding oil is theta 1, and not finding oil is theta 2, because not all the oil that wells that are drilled end up being productive and producing oil. Before he makes his decision to drill or not to drill, the wildcatter can decide maybe to seek help from some geologists, and he gets, in that case, he gets geological, geophysical evidence by running some experiments. And this is called some kind of really trying to gain information about the formation underground that he is planning on drilling through it. So he hires a geologist, and in that case, he runs a geological survey, and or he decides not to run a geological survey, just saving money, and maybe he's very sure that that formation there contains oil, because maybe there is oil bubbling on the surface of a pond, water pond, where he knows that there is oil underground. So this is another space of interest to us. Again, we take it as a binary state, where either that he runs a geological survey or he doesn't run a geological survey. So you can see here, there are decisions to be made to reach the final outcome, either that he finds oil or doesn't find oil in general. And we can simplify the system again by allowing for only one of experiment. He can take seismographic recordings. So in exploration for oil, what they do is that they explode an explosive at the surface. They let the shock wave propagate from the explosive into the ground. And then, of course, if you have a formation underground, the shock wave from the explosive coming from here, if you have, say, here a formation that contains oil here, let's say that the oil is contained in that formation here, the shock waves are reflected back and they are measured. So that would have huge trucks in that case. Let's show a truck here and with large wheels, and they explode many explosives, in fact, and then they look at the reflections from the shock wave to decide whether there is a formation, maybe here a trap where oil is trapped in the ground, and on top of it's a natural gas through the reflection now of those waves. This is another problem that we call an inverse problem of mathematical physics. You are not interested in the attenuation of the shock wave. You are interested in the shape of the shock wave as it reflects, and then you use sophisticated computer programs to get some kind of a total, really, description of the formations underground, where you can see whether there is a trap where the oil could have been trapped. So let us say that those readings give us a detailed description of the formation that is underground in that case. Now, let us give it 4 type of options, not just 2 options. Z sub 0 would be that there is no geological survey results available. Z1 as there is no subsurface structure, so he doesn't have that dome shape underground that would trap the oil. Z2 would be there is an open subsurface structure, and Z3 would be there is a closed subsurface failure. Obviously, you'd love to have that 3-3 occur. Now, in that case, let us suggest that these are the 3 kind of decisions that the wildcatter has to do. And in the end, he has to get another space now to decide whether he should drill or not drill. Now, at each node of the trees that we are going to discuss here, he adds a utility function in statistics. So he gives a value for that Z2, Z sub 0, Z1, Z2, Z3, and he ends up with what looks, in fact, as a tree. And that's a decision tree. So in the first part of the tree, he had one or two decisions to make, E sub 0 and E1. If you remember, E sub 0 or E1 was the whether he runs a geological survey or no geological survey. Having decided on this, he goes to the other level here of the Z decision-making part of the tree, which is no geological survey results. Oh, that eliminates really the subsurface structure, or here the 3, Z1, Z2, and Z3, and he goes only through Z sub 0, or he discovered that maybe there is a subsurface structure. So he's faced with the Z1, Z2, Z3 as an outcome. Having gone through that Z1, Z2 as an outcome, he goes to the decision making of A. Here, A1, A2, drill or no drill. And in that case, in the tree, you'll find that the branch here splits into A1 and A2, A1, A2, A1, and A2. And in the end, if he calculates the utility, that's called the utility value at each node, he can multiply or add the utility at each node. And in the end here, he gets the outcome theta 1 or theta 2, which was that he finds oil or he finds no oil. Each one of those paths has its utility value. And in that case, instead of just going every time and drilling, you have the input from the geological survey and the input from, say, a geologist and so on in the decision process. Notice here that you start from a point here and then you end up with branches of a tree. And the more decisions or branches in the tree that you have available to you, you get what we call a combinatorial explosion, in that those branches become so large in number that it's very hard to make a decision. That's why we're going to find ways of pruning the tree. In fact, he pruned that tree here, if you could see here, in that branch here, he simply eliminated the possibility of Z1, Z2, and Z3, and he went only for Z sub 0. So decision trees have been used in operations research, in statistics, to make decisions about different alternatives if we have to go through them. So the decision space then can be described as the E, Z, A, and A. And notice that the three possible outcomes of the subsurface structure corresponds to the states Z0, Z1, Z2, and Z3. And the outcome, the total outcome is theta outcome in that case. As I suggested, at each node in the decision tree, you assign utility values that you can add. You don't need to, but you can add utility values depending on how much money you spend, say for a geological survey, or in the case of drilling or not drilling. All right, this concept of decision trees from operations research has been adopted in the concept of what we call now a different concept we call event tree analysis. And event tree analysis, interestingly enough, is more or less like a Boolean type of an approach, in that either that you have a success state or you have a failure state. So this is a binomial distribution, as it's called, like you have one state and its opposite, or only two states, success or failure state. You identify then an initiating event. And if we think, let's think maybe now in terms of a more engineering approach, an initiating event could be an earthquake. Oh, let's think Fukushima. The earthquake occurred, and that is what we call an initiating event. So in an event tree, we are going to always identify an initiating event. The initiating event does not cause damage to our engineered structures. We are thinking in general for any engineering structure, but you'll find that the different components behave differently. So for instance, the earthquake can cause a tsunami, or it cannot cause, if it's too mild, maybe it doesn't cause a tsunami, and so on. So what you do in that case is, after the initiating event, you think about other events that can happen, and that generates basically, after the initiating event, a sequence of events. Try to remember the terminology here. An initiating event is followed by a sequence of events, and all of them are binary. It could be either a success or a failure. And to avoid the situation where you have that binary explosion, is that you can have a tree that have many branches, we eliminate the events that are not logical. So if you don't have electricity in the plant available to you, like in Fukushima, then your safety systems and your control systems and your control room are not going to work anyway. So you cannot assume that they'll continue operating. So in that case, that prunes the tree to avoid that combinatorial explosion that could happen to us. So we prune the trees of any illogical accident sequences. So we start, again, I repeat, an initiating event. The initiating event is followed by accident sequences, and the accident sequences can be very large. We prune the tree of the illogical accident sequences, and then for each one of those events, we assign, in the state of art that we have today, probabilities of occurrence, maybe because we have observations, we have measurements of events that happened in the past. If we don't, if we are depending on models or the ideas or opinions of experts, then in that case, we use possibilities rather than probabilities. And then we apply the mathematics to calculate the probability of each branch of the tree occurring, or if we don't have the actual observations, then possibility theory comes to our help, and we can calculate a possibility in general. So let's look at how we can show this as a graphical representation. It is not exactly the same as a decision tree as you see here. We start with an initiating event, let's call it I. And then we have different components or different parts of our plant, or a skyscraper, or a bridge, or a refinery, any kind of engineering structure. And even it can apply also to social systems, like it can apply to a field of economics, like, oh, stock market crash, or the stock market goes to a maximum, or similar situations. But for each component, we assign a success state where it succeeds, or a failure state where it fails. And now that's a component number one. The component number two also can have a success state or a failure state. We designate the success state as S sub 1 and the failure state as F sub 1, S sub 2, and F sub 2. You could see here the tree already has branched from an initiating event into four. For two components, we have already four possible branches in the tree. We designate the occurrence in that case as an initiating event, and the success state in S1 by this, and the success state of S2 here as I S1 S2. If we can follow the branches, this is I F1 S2, and you could it is saying basically that we get an initiating event. The first component is successful, but the second component fails in its operation. Notice that we said this is a binary kind of a system. So we are not interested just in designated the accident sequence. We are interested in calculating what's the probability of these four accident sequences occurring. Notice that implicitly we said that we have an initiating state followed by success state, followed by a failure state. So there is here an implicit AND gate. We are an implicit AND gate. And we said in probability theory, if you have an AND gate, and you have two events, the probability of event 1 multiplied by the probability of event 2 is the probability of both events 1 and 2 occurring. So in that case, we turn our tree here into a sequence of probabilities, and we assign for each branch in the tree a given probability, the probability of the initiating event and the probability of failure. We are thinking about failures here in that case at the design stage. So that's a probability of failure of component 1, the probability of failure of component 2. And because we said that we assume that the event, initiating event I and F1 do occur, so you'll find that we are multiplying the probabilities. Remember that there is an implicit AND gate. Now, if there is a failure, what is the probability of success? Well, because it's a binary state, one or the other, the sum of the probabilities should add up to 1, either that it fails or it operates or succeeds. So in that case, if the failure state has a probability P of F1, the success state is 1 minus P of F1. And if you add the two of them, of course, one or the other occurring is equal to 1. So in that case, we can calculate the probabilities of each one of the three occurring. If you move along the bottom line, that's P sub I multiplied into the failure of the first component, the probability of failure of F1 multiplied by the probability of failure of F2. If you move to the top component, is the probability of the initiating event here, multiplied by 1 minus the probability of failure of 1, multiplied by the probability of success, which is 1, minus the failure of component 2. So in that case, we can move along each branch of the tree and calculate a probability of each one of them occurring. All right, so let us think about possibilities. So let me go back to the theory here. We have basically invoked the fact that in probability theory, if you have a binary state, two states, then the occurrence of one of them should be equal 1 minus the other, because the two probabilities should add up to 1. So the probability of success is 1 minus P of the probability of failure. All right, and then we invoke, of course, the probability of I and F1 and S1. We have learned that from probability theory, when you have two independent events, the probability of A and B and C occurring is equal to probability of A multiplied by the probability of B multiplied by the probability of C. If you forgot that simple law, think about throwing a die and tell yourself, what is the probability that I get snake eyes? Snake eyes, if you go and gamble at Las Vegas, means that you get a 1 and a 1 on both dice that you throw on the ground, and each one of them is 1 6 and 1 6. So you know that the probability of you getting 1 and 1 in throwing a dice, a pair of dice, is 1/36. It should be a small probability than either one of them occurring. So in that case, we multiply the probabilities as we move along the branches of the tree. This looks like complicated, but in fact, you'll find that it's very simple when you apply some numbers to it. Now, I want to hit two birds with two stones. If I have probabilities of failure, say I know how often a phone fails, and we have data for components like the phone, the door on a car, the starter on a car not starting, then we use probability theory, because that is based random variables like failure rates are all follow the laws of probability theory, because they depend on actual measurements, actual observations. What if you're in the stage of designing a car or designing a new power plant? You haven't run it yet, so you don't know what's the probabilities of failure. You don't have data. So in that case, you use models. You can have a model on a computer, and in that case, it is not, I repeat, probabilities unless you have measurements. it is now a possibility. So in that case, we can design a tree that depends on possibilities. You can say, what is the possibility of the initiating event? Then you have the possibilities for the different components, either succeeding or failing. So let's say the success, the failure state is in possibilities for component 1 is pi of F1. This is capital pi. The probability of the possibility of failure of the second component is pi of F2. Obviously, the success state would be 1 minus the possibility of failure. So that would be 1 minus pi of F1, 1 minus pi of F2, 1 minus pi of, that should be of, F2 and F2 right here. So if you want to say what is now the possibility of the initiating event occurring and the first component succeeding in functioning, like the pumps turn on or the voltage goes up and you have current, then in that case, the possibility of the initiating event occurring and getting in the success state and another success state, as we suggested, the AND gate in possibility theory is the minimum between the three possibilities. Try to remember that law. So in that case, it is a minimum between the pi of the initiating event, 1 minus pi of the success of the first component, and 1 minus the pi of the second component. So if it is, this is 0.3, 0.2, 0.1, the minimum of 0.3, 0.2, and 0.1 is 0.1. So this is when we do calculations using possibility. And I would like to point out again that possibility theory applies at the design stage or the conceptualization stage as a prediction or anticipation method. Probability theory applies when you have data that has been accumulated or frequency distributions, actual observations of devices that we design. And so in that case, in fact, probability theory applies when you are operating the system because you have data about its operation. Possibility theory applies when you are at the design stage. And some people mistake the design stage and use probabilities when in fact what they're really using is possibilities, because we don't have observation. So whatever data they have are really possibilities. They are not probabilities, yet you find papers published and making that mistake. I hope that you'll be able to correct this in general. All right, now we need to do this in a quantitative way. This is a qualitative description. You'll find that in terms of the probability of failures or the possibility of failures, as engineers, we don't go and design systems that will fail with a failure rate of 1/10, meaning that, say, the door on your car would fail to open or close once every 10 times you use it. That doesn't make sense at all, right? Nobody will buy your car. Or you have maybe the starter on the car would not start your car 9 times every 10 times you start the car. So when we design meaningful engineering systems, the probability of failure have to be less than maybe 10 to the minus 3 or 1 in 1,000 or 1 in 10,000. So the probabilities of failure here for meaningful components in engineering should be very small. Otherwise, we cannot sell them. Nobody will buy them. No one would want to even operate them. So in that case, you'll find that those probabilities of failures here are very small. Let's say, for the sake of example, 10 to the minus 3, meaning that they fail once in 1,000 times, or the failure on demand, it's called, is 1 in 1,000. So when you take 1 minus the probability of failure, 1 minus 10 to the minus 3 here, it will be 0.999. If it's 10 to the minus 4, it's 0.99999, 4 nines. So in that case, it's approximately 1. So in that case, for engineering purpose, instead of having to write this very complex kind of sequences, probabilities, and possibilities, we make what's called the small probabilities approximation. We are approximating the failure, if I know the failure rate, success rate, if this number is meaningful, meaning very small, is approximately equal to 1. So the success rate is usually taken as 1, provided that the probability of failures are small enough. So this is what we call the small probabilities approximation in general. So here it is. We are going to use the small failure probabilities. And if the possibilities also of failure in our components are small, then the 1 minus the possibility of failure is approximately equal to 1. All right, so this is now a way of us for doing some actual computations. So we modify our event tree by saying that I get an initiating event, a probability of failure of the component number 1, and the success state. If P of 1 is small, very small, then this is equal to 1. So don't go and in a test or in an assignment and write me 1 minus 10 to the minus 4, and then you write 0.9999. Well, any computation will give you 1 anyway. So in that case, we approximate it as 1, the success rate, provided that the probability of failures are small. This is basically a way of making our event trees some kind of simple. And simplicity in engineering gives us insights on how systems operate and function. If we simply try to put in all the little tiny detail, we lose the overall picture. We basically get lost in the forest by looking at each one of the trees separately. So in that case, you could see here now that the probability of that sequence, that the initiating event, but then an engineer safety features, the pumps turn on, then the voltage recorders are on, everything is fine. You'll find that instead of having P of I multiplied by 1 minus P of F1 minus PF2, you find that P of I multiplied by 1 is P of I, and this is P of I by PF2. So you could see here now that your tree is highly simplified. And instead of having that whole sequence here, this is 1, this is 1. So this is P of the probability of the initiating event, and the tree is simplified. So simplification is in the essence part of good engineering in general. The same will be done for the possibilities. So you'll find that also we have that small, in the same way that we have a small probabilities approximation, we have a small possibilities approximation. And this is the first way of simplifying the process. Why is this? Because usually if you are dealing with engineering components, they're very complex. They don't have only 2 components that are faced by an initiating event, an earthquake. You'll find that you may have maybe a human error, you may have design flaws, and the system can grow with many components. We'll look at an example. In that case, it becomes totally unmanageable. And the same for the decision trees. You have to prune the tree. So we'll see how we can do this. So let us take as an example a typical accident that happens in nuclear power plants. And we call this the loss of coolant accident. Oh, that loss of coolant accident happened in the 3 Mile Island accident. It happened in the Chernobyl accident. And it happened also in the Fukushima accident. If you do not cool your plant, even after you shut down the fission chain reaction, you still have those fission products generating radioactivity, beta particles, electrons, and gamma rays for at least 24 to 48 hours. And if you do not cool them, if you have a loss of coolant accident, designated as LOCA, this is the acronym for it, LOCA, loss of coolant accident, you melt your core. And that's what happened in the 3 Mile Island. It happened in Chernobyl. It happened in Fukushima, because we are still stuck by using solid fuels in those types of reactors. If we switch to liquid fuels, then in that case, we can eliminate those fission products, and we wouldn't have the equivalent of the 3 Mile Island. That's why I'm advocating that we should switch to liquid fuel. If you have a liquid fuel, you continuously extract those fission products, and you basically eliminate the possibility of the 3 major accidents that happened. But let us say that I have a nuclear power plant, and we want to generate an event tree that may happen maybe after an initiating event. And let's think about the Fukushima maybe accident, but I'm not describing Fukushima here per se. So let us take a nuclear reactor, and a simple one because it's much more complex than what I'm showing you here. And we get an initiating event, let's say an earthquake, and we are not considering tsunamis or anything, but another component after the initiating event, you can have the electrical power availability. And that happened at Fukushima, in fact, because at Fukushima, the earthquake destroyed the system on the plant itself that was producing power. It flooded the basement of the whole reactor. It was not designed adequately. It was too close to the surface of the water. They had a hurricane kind of a barrier, but it could take waves from hurricanes, but not from a tsunami. And that's why they lost the power, because their electrical equipment, the safety equipment was flooded. It was the first time ever really that we had a flooding accident in a power plant. And in that case, they lost the power at the plant itself. However, all nuclear power plants have also another connection. They are connected to the grid. Some plants even have two connections to the electric grid so that they can get power from the outside. If you lose the power at the plant and the power from the outside, from the grid, we call this a station blackout. The station, the power station goes totally black. The control room have no light. You don't have electricity. So that is a major type of situation in that case. So let us say that you get an initiating event, and then you look at the electric power availability. Do I have electric power? Success, oh, it's 1 minus the probability of failure. The probability of failure is small. In that case, we write it here as 1. Then we go and think about, all right, if you don't have the electric power, all nuclear power plants have that emergency core cooling system that we considered in the cost-benefit analysis chapter. We have diesel generators, not connected to the grid, so they don't need electricity from the grid. They don't need even electricity from the plant itself. They use diesel fuel. They start generating electricity for powering the plant and running pumps that bring in coolant, replacing the coolant that could have been lost. We call this emergency core cooling system. And it can succeed. If it succeeds, it's 1. If it fails, it's P of B. We are calling the initiating events I, the electric power availability, capital A, the emergency core cooling system, capital B. Then you start thinking now, if this one or this one do not work, and the fuel starts melting, so the fission products, the radioactivity, would be released from the fuel. And we have systems there that would filter the exhaust or the plant's air circulation on beds of activated charcoal. So all the gases that are radioactive would be deposited there. And this is what we call the fission product removal system. And so that is another safety feature in existing nuclear power plants. Following that fission product removal system, we have the containment structure. If radioactivity is released, it is contained inside those big 6 feet thick concrete structures that are a steel lining on the inside, or they can have, in fact, some plants have a refrigeration system having ice. They call it an ice condenser that would intervene with any steam release inside the containment structure and simply quench the steam generated, because the pressure of the steam can eventually lead to leakage from the plant itself. So we have here an initiating event followed by 4 different kind of safety systems. We call them engineered safety features of the plant. And you consider that either that they succeed. So you get an initiating event, the power supply is available. Oh, it succeeds. So it's 1. Emergency core cooling system succeed, it's 1. The fission product removal success is 1. The containment leakage is 1. So the probability of the initiating event occurring and everything else working fine is obviously an AND gate, and the AND gate multiplied the probability. So the probability of the initiating event multiplied by 1, by 1, by 1, by 1 gives you the accident sequence probability as P sub I. Now, what if some of those components fail? So you'll find that here at each component, the A, the B, the C, and the D, we have a failure probability right here, a failure probability for B, a failure probability for C, a failure probability for D. So you get here now, in the decision tree, all those branches. And notice how quickly you build up those branches of the tree branches very quickly. If you add more like 10 components, you'll find that you get what we call a combinatorial explosion in that case. So in the same way as in decision trees, we need to prune the tree. And how do you prune the tree? You eliminate any branches that are not logical to occur in that case. And this is part of the technique itself of event tree analysis. So in that case, we talk about a pruned or a reduced event trees, and we go back to the availability of the power, electric power availability, and that's what happened at Fukushima. They lost the electrical power from the plant. They also lost the electrical power from the grid because the earthquake affected a transformer station 8 kilometers from the plant. You can have fun and simply go to Google Earth and follow the lines that are bringing the electricity from the grid to the Fukushima plants. If you don't have the electric power available to you, well, you cannot run the emergency core cooling system. You cannot start those diesel generators. You cannot have a project removal system. So all that part here of the tree can be pruned if you don't have the electric power available. That's in fact called the station blackout. Then the probability of failure is the probability of initiation event multiplied by 1. And oops, you get here the probability of, that's a success rate. But if you have a failure of the power system, in fact, at the bottom here, then definitely radioactivity is going to be released from the plant. Now, in general, why do we need this? Because basically, if you have many, many components, the system becomes so overwhelmingly unmanageable that you lose insight into, if you go into the whole detail. You want to get the overall picture. You look at the forest, not at each individual tree. And in that case, if you have basically n components, you'll find that if you have 4 components like what we have done here, let's look at our diagram. We have 1, 2, 3, 4 components. The combinatorial equations in mathematics tells me that the number of branches would be 2 because we are taking a binary system, failure or success, to the 4th power. Oh, you get 16 branches. And see here, you get 16 branches, 4, 8, 12, 16. Now imagine something that has 10 components, and this is really the reality of it. Then you have now 2 to the 10th power branches. So in that case, it's so overwhelming, we lose insight, so we need to prune the tree. And as I suggested, so for instance, if you lose your power supply, oh, you cannot start the diesel generator, you cannot start the emergency core. And actually, if the emergency core cooling system also fails, you cannot run the fission product removal system. You cannot get rid of the containment leakage also system. So in that case, you prune the tree, only the top part of the tree where you can have the fission product removal and the containment leakage under your control. So your 16 branches of the tree now are reduced to 2, 4, 5, 6, and this is what we call a pruned tree, a pruned event tree. And we can plug in some numbers in it if you want. In terms of possibility theory, it's also the same approach. I'll give you a small problem where I ask you to plug in some numbers here and calculate for a probability theory the product of the probabilities. because we have an implied AND gate, and for a possibility theory, it's a minimum between the possibilities of failure for the pruned tree. How do we construct event tree? As I suggested, it's an art and the science. We've learned a little bit about the science. You start by the definition of the initiating event. That's very important. You identify the relevant component in the system, and that is means that you know about how the system functions. You enumerate the failure and success states. You create a basic event tree. You prune the tree by accounting for logical events. You get the pruned or event tree, and you are ready to calculate the probabilities or the possibilities of failure. Some very interesting aspect of fault tree analysis is how do we determine those probabilities of failure here and here and here. And it's very interesting. We determine them by, what do you see here? This is a fault tree. Do you see that? A fault tree. So in that case, when we do the safety analysis of power plants, we do not just use the deductive logic, the fault tree analysis, or the inductive logic only. You could see they're combined they're combined together. The event tree is here, and the probabilities of failure, all of them are determined by fault trees. So we use a combination of deductive and inductive logic. The same if you read the books or watch the movies of Mr. Sherlock Holmes. So in that case, I come back to the diagram that I put on the board at the beginning. You create general hypotheses. If you use the deductive logic, you move from the general using fault tree analysis, using backward chaining to the basic events or data. If you use inductive logic, you start from the bottom. The specific data, you do forward chaining, you use event tree analysis, inductive logic, and in fact, we combine both of them, and I'm giving you an exercise to plug in some number yourself to see how much fun it is to build event trees and a combination of event trees and fault trees. And here we have learned another method for basically the probabilistic design of any complex system, not necessarily just nuclear power plants. Thank you for your attention. If you have any questions, I'll be available to answer them.